So we're going to talk about reinforcement learning today, which is a very different flavor of machine learning than what we've done so far. So, excuse me. The simplest sort of vanilla flavor machine learning we've done so far is input-output, typically in the context of concept learning. So you're learning just a binary output, yes or no. Or in more general, given an input, produce an output. We generalized it a little bit when we talked about Markov models and hidden Markov models, because then it was not a single decision that each time was separated from any other decision, but it was a system evolving in time, and at any one time you can stop and ask yourself which state do you think the system is in, and you can make your guess, either a hard guess or a posterior, and then you can move on to the next step and ask that question again. So there is a notion that the system is continuously evolving. What we're going to move to now is even more in that direction. We are in a system that's continuously evolving, but two things are going to be different and more difficult. One is that we're not going to only make predictions or guesses, we're also going to make decisions and take actions. And our actions will have an impact on where the system is going. So in the case of hidden Markov models, you could guess all day long, but it doesn't change where the system is going. It will not change the future of the evolution of the system or what output you see from the system. Your predictions don't interfere, don't do anything to the system. The setup we're going to talk about today is where your predictions or your reasoning or your decisions ultimately do affect how the system evolves, although not necessarily in the deterministic way, and not necessarily in a way that you know in advance how they're going to affect it. So the one big difference is we're not only making predictions, we're actually taking actions, and these actions affect the system evolution. The second difference is that until now we measured our success in how well we predict things. So our error rate, classification error rate, or mean squared error, or anything like that. But this measure of goodness or accuracy or correctness was applied independently to each instance, to each input. Input, output, input, output. Each one, either you were right or you were wrong, and you can average how many times you're right. What we're going to do now, today, is look at our cumulative success, or cumulative reward, which is slightly different in the sense that, I suppose if you look only at your average accuracy, it's also somewhat cumulative. But it's cumulative in a way that is not linear, in the sense that we will weigh our immediate or short-term reward more heavily than reward that's further out in the future. So it'll become clear as I introduce it more formally, but I'm trying to sort of give you the motivation. So the setup we're talking about is called reinforcement learning setup or policy learning setup, is when the system is trying to navigate in a space, typically a very large space of states. It could be a finite number of states, could be a continuous space of states. And at any point you have to make a decision of what action to take. Once you make the decision, the system moves potentially to a different state and potentially gives you a reward. And then you repeat again your decision of what action to take next. You take another action, you move maybe to another state, and again you may get a reward. Sometimes you get a reward, sometimes you won't get a reward. In the same state, the same action sometimes would lead you to one state, sometimes would lead you to another state, if the system is non-deterministic. If it is deterministic, then being in a given state and taking an action will always lead you to the same state. So there are some varieties, some flavors, different flavors of it. Now this may sound abstract, but actually there are lots of real-world situations that conform to that. So think about a robot trying to navigate a room. Specifically, the first thing a robot needs to learn is to charge its own battery. Right, that's the first trick you need to teach a robot. Well, how would it charge its own batteries? It has to know where are the outlets for charging, where it is right now, and what's the best way to get to one of these outlets. So you can think of the state of the system as the state of the robot in the room, exact coordinate. The actions could be something as abstract as moving to the right, left, front or back, or something as specific as turning on a particular motor or servo, or moving, keeping it on at a certain speed for a certain period of time. It could be low level or high level, whatever. The interesting thing about it is that taking the action, such as moving some of the motors, takes you to a different state. But it may be in a deterministic or a non-deterministic way. With robots, it's almost always non-deterministic. Unless they are simulated robots in a finite deterministic environment, anybody who's worked with robots would tell you that what you tell them to do and what they do is a totally different thing. And you can issue the same command to the same servo, to the same engine, same motor. One day it'll move this much, another day it'll move that much. You really cannot predict exactly what it would do. So here you have the situation where you take actions, you change the state of the system, but in a way that's not deterministic, and it's not necessarily completely known. You could argue, you can reason, you can infer about it, but you cannot be sure what it would do. Now in this case, in the case of a robot, your rewards are all absent until you get to the outlet, and then you get plugged in, and then you get a big reward, getting a lot of power. Right? There could be other situations where your rewards are collected along the way. Suppose you're collecting strawberries in a strawberry field or raspberries in the forest. Your actions are which way to move, which way to move your head, which way to move your legs, and your rewards come along the way. And ultimately you measure your success in how many raspberries you collected. Now the interesting thing here is that there's a trade-off between short-term gain and long-term gain. Suppose you're in a patch that has a reasonable amount of raspberries, and there's another patch that you believe, but are not sure, has a lot more raspberries, but it's 100 yards away. So are you going to stick where you are, collect the short-term rewards, or are you going to invest in taking a trip, a 100-yard trip, during which you will not collect any raspberries, so that later you can collect more? So there's a trade-off between short-term and long-term. There's also a confounding effect, which is that you're not 100% sure that that patch is better. In fact, imagine a situation where you are in a patch that's kind of okay, there's raspberries here and there, and you don't know what's out there, except you know that there may be better patches somewhere. Are you going to devote the time to looking for them? I mean, that's the situation we're in all the time, right? Are you going to explore better alternatives, or are you going to stick with the alternatives you have? These are decisions we are facing all the time. If you drive a car, or if you walk from your home to school, you may have found a path that you prefer. But especially in the first year here, you may have wondered, is there a better path? Especially if you drive, it's not clear which path is better because of traffic conditions. So if you're a little adventurous or you like to explore, you might say, okay, I know this is pretty good, let me try this other path. Most likely it's not as good, but there is some chance it's better. Somebody else might say, no, this is good enough, I'm not going to try. Personality comes in, of course. Your risk aversion, adventurism, whatever you want to call it. But another factor that comes in is, for what time horizon are you optimizing? If you're only going to be here for another 2 weeks, maybe it doesn't make sense to go out exploring, because chances are it'll take you more time. But if you're going to have a career here and stay here for 20 years like I did, then maybe it's worth trying to shave off a few seconds here and there. It'll accumulate. And then some people don't care how long it takes them, so that's altogether different. So this trade-off we'll come back to many times. I don't want to give you the name for it. It often goes by exploration versus exploitation. So you found a nice patch of raspberries, you're going to exploit it, or you're going to invest in exploring that might give you better rewards later. Okay, back to formal reinforcement learning. So I gave you the example of the robot. Reinforcement learning problems come up in many real industrial situations. So the typical example is factory that makes, one factory I remember visiting in Israel once was making plastic bags, like the kind you use to line your garbage cans. They were specializing in that, and it's made of this polymer plastic, and they had these machines that constantly measure the thickness of the plastic that's being generated and other properties of it, and adjust the contribution of different components and temperature and speed and whatever. There's no good analytical model for doing that, for optimizing that. They have to constantly measure it and constantly update it, and the update itself, it was not clear what effect it was having on the outcome. So you can again think about it as being in a certain state space and having to make decisions, and decisions affect your next state, but you're not sure exactly how. There are lots of such examples in factories. Factory output is often a reinforcement learning problem. Another interesting example is games. I think I discussed chess or backgammon with you at the beginning of this course, did I? I usually do. I don't know if I did it this time, but chess and backgammon and other... I did. Thanks. It's good to have you here. So you can think of chess and backgammon as reinforcement learning setups where your reward is all the way at the end. Right? If you remember, the kind of reward you get in something like chess is you get no reward along the way, and then if you win you get a large reward. If you lose you get a large negative reward. If you draw you get 0. And that brings up another problem. Anybody guess? What's the problem that's introduced into learning when your rewards are all at the end of a long path? Please?
Well, you can't tell where you went wrong.
Yes, and what name does it go by in AI? Credit assignment or credit blame? I'm sorry, credit assignment or blame assignment? Credit, blame, assignment. The idea is that the outcome of the game is the result of many decisions you made along the way, as well as decisions made by your opponent. Some of these decisions may have been good, some of the decisions may have been bad. Generally speaking, if you lost the game, you could conclude that you must have made at least some bad decisions. And if you lose a lot of games, you can conclude that you make more bad decisions than good decisions. Even that is a little iffy. But that's all you can say. You cannot point to any specific move in the game and say, well, I lost, therefore all my moves are bad, or this move is bad. You may have made very good moves, and in fact the outcome of the game is very non-linear. So you can play brilliantly for 39 moves, and then make one colossal mistake on the 40th move, and you lose. So learning from the outcome of games is very, very hard, because you don't know which of your moves are to blame, or if you win, are to be credited. So that's going to be a problem in all setups when our reward is delayed. But the setup in the game where you get no reward during the game and a huge reward at the end is an extreme case. You can think of other more moderate cases where you do get rewards, but still the reward that you tend to get later is influenced by something you did earlier, and it may be influenced in a subtle way that is hard for you to detect. So if you go back to the raspberry patch, you may not realize that you're wandering through a raspberry wilderness with no raspberries for a while, and you think you're doing the wrong thing, but actually you're moving towards a wonderful patch, and eventually you're going to get there and reap the benefits. So as you can probably tell, this is a very, very hard problem, and often it'll lead to intractable situations where there is no known algorithm, and we suspect there are no algorithms that would give you optimal behavior. Maybe the surprising thing is that there are actually situations where you can prove, you can give an algorithm where you can prove that it will eventually learn optimal behavior, which is amazing, given the difficulty of the delayed rewards and not knowing the state space and not knowing how your actions affect the state. But the twist or the trick here is the word eventually. What we can typically prove in reinforcement learning is that the algorithms we use will eventually, asymptotically, after a lot of exposure, converge to the optimal solution, but that asymptotic thing will never arrive in your lifetime. It will just way too long, even for small problems. Even for problems with a handful of states, it could take forever. And for real world problems, forget it. So this is generally the state of the art in reinforcement learning. It's a very useful setup, very commonly encountered setup. A lot of math is understood about it. We have algorithms that are guaranteed to converge to the optimal result. When else did we have it in this course? I mean, it's wonderful, right? But it's guaranteed to converge, at the end of eternity. It's not at a reasonable amount of time. So of course there's a lot of work on trying to make it converge to something reasonable in a reasonable amount of time. And that's when it becomes fuzzy and not so clear. Okay. So here's a formalism of what I've just described informally. Just copying it from the slides. Here is the agent, that means you, or your computer. Or the learner. Here's the environment. So that would be the forest with the raspberries, or the room for the robot that's moving around. And now it's a two-way game. Unlike machine learning until now, when the learner was just an observer, just making predictions and not affecting the system, now it's really a two-way game. On one hand, the agent can take actions. So we will typically assume that you have a choice of a finite number of actions. There is a generalization where your actions come from a continuous space, as in take a step that's 5.3 centimeters or 5.4 centimeters or any number in between. But for simplicity, for the rest of this talk, we'll talk about a finite number of choices to choose from, of actions. So the agent, you know what your choices are. You don't know what they're going to lead to, you don't know if they're good or bad, but you know you formally have a fixed set of choices, you can choose one of them. Once you take your action, you affect the environment. The environment moves from whatever state it was in to another state. And it communicates that movement to you, so it tells you the new state it's in. And it also gives you a reward, which often can be zero. We would typically assume that rewards are non-negative, although it's fair to create a setup where rewards could be negative. And we need to think about, does that change anything in our algorithms or in our analysis? But typically rewards are non-negative. So the worst thing would happen is you would not get no reward. Now, if you the system starts in state, let's say S0, the agent makes a decision, let's say action 0, some action. I'm calling it action 0, it's the action that was chosen in state 0. The index here is a time index. So S of 0 just means the state at time 0. It could be any of the states. The system responds by giving you reward R0 and moving you into state S sub 1, some state of time T1. S1 could be equal to S0. It could be the same state as in the loop, or it could not. It could be something else. And again, you choose some new action, say A1, and the set of actions available in this state might be different than the set of actions available in this state. So it could be that you have a finite set of actions that are available in all states, but it could also be that in different states you have a different choice of actions, and some of them overlap, some of them don't. You were at S1, you took action A1, you were rewarded by reward R1, and you moved into state S2, and then you took action A2, got reward 2, moved into state S3, and so forth. Now what are we trying to learn? What would we try to learn here? Any suggestions?
What are the series of actions that we can take?
What is the series of actions that we could take? So I'm assuming that you are given at any state what actions you can take. Or maybe I interrupted you too soon. Finish that thought.
At each state we have several different options.
Right.
We have a certain goal, and so
what's our goal?
a goal, I guess, is generally specified.
I'm sorry?
A state, perhaps. A final.
Reaching a certain goal state. Okay, that's fine. So you can imagine that your states are all over the place, and there's one particular one that's our goal state, and that our goal is to get to that goal state. That would be one possibility. Any other possibilities?
Get to the goal state with the most rewards.
Get to the goal states with the most rewards. Okay. So I want to suggest that it's enough to focus on the rewards. And in a minute I will fold in the goal state into the reward. I want to suggest that the rewards are the most general formalism, because you can always choose, if what you care about is just the goal state, you can always choose to always give a large reward when you enter the goal state and give no rewards any other time, and also make sure that you cannot leave the goal state. You can set up the system such that when you're in the goal state you cannot leave anymore. As a result, the only game in town would be to get to the goal state and get your reward. If we did that, there would still be a problem that a method of getting there in 5 steps or a method of getting there in 100 steps would be viewed the same way. You got to the goal state, and we don't want to view them the same way. We want to get there as fast as possible. So one way of achieving that is to make the rewards, to discount the rewards in time. Namely, to weigh more heavily rewards that you get sooner than rewards that you get later. So imagine a situation where what you want to do is learn to get to the goal state as quickly as possible. You can implement it via rewards if you use the reward system I suggested, namely that you never get a reward except when you walk into the goal state. Once you walk in the goal state, you get a large reward, and you're not allowed to leave the goal state. And in addition, the reward that you get when you walk in the goal state depends on how many steps it took you to get there. Now that's a little complicated. How are we going to implement that? So the way we're going to implement that is by accumulating the rewards. We start with 0 here. Reward 0 plus reward 1 plus reward 2 plus reward 3 and so forth. But we're going to discount them in time. We're going to declare a discounting factor, which we call gamma, which is smaller than 1 and larger than 0. So it could be typically something like 0.9 or 0.95. And we're going to discount the rewards every time step by this amount. So R0 is going to be counted fully, but R1 is going to be replaced by gamma times R1. So only 90 or 95% of R1. And this is going to be replaced by gamma squared times R2, gamma cubed times R3, and so forth. Those of you who took electrical engineering can start thinking of leaky capacitors, only backwards in time. So we can define our cumulative reward or cumulative discounted reward as this thing, and there are many reasons to introduce this discount. One is the example of the goal I told you. You want to get to the goal quickly. Another one is that if you don't introduce this kind of discounting, this sum is not well defined. It goes on to infinity. You need to find a way to chop it off somewhere. You could say that the game only goes on for 100 moves. That would be okay. But if you want to talk about optimal control strategies in general, you want to look at the expected reward going on from now to infinity. A very similar situation occurs in financial planning, where if you try to assess the value of a company, you try to think about the sum of its expected profits from here to eternity. If you're going to buy a company or buy shares in a company, you want to evaluate a company. You want to look at how much it's likely to earn this year, how much it's likely to earn the next year, and add them all up. And of course, it's not going to add up to infinity. I mean, if a company is profitable, and you believe in it, and you believe it will continue to be profitable, then it should have infinite value, because every year it produces money, and you still own it at the end of the year. So where's the catch? Well, the catch is in that there is uncertainty, and the uncertainty gets larger and larger as you move further into the future. I mean, Microsoft is a wonderful company, but I'm not sure what it will be 100 years from now. Right? For just about any company, even very stable ones, you're not sure where they will be X years from now as X grows. So this notion of discounting the value of money is very, very prevalent in financial planning and financial models. There are other reasons for it. Inflation. If you nominate value in fixed currency, like US dollars, the value of the dollar goes down because of inflation. But that's not the only reason. Even if you live in a world or in a country where there was no inflation, you would still need to discount future values because of the uncertainty of, are you going to get it? There's always a possibility the company will go under. There's also a possibility something else would happen and become profitable and so forth. So $100 today is worth more than $100 10 years from now, not just because of inflation. Also because today it's in your hand, and 10 years from now, who knows? Right? There's always risks and uncertainties in the legal system and the political system, and it could be a nuclear disaster tomorrow, who knows? So this notion of discounting future rewards is very fundamental. And it's fundamental to the way we think, too. There are quite a few anthropological and sociological and psychological studies that show that people do use discounting of future rewards in their own decision making. People sort of intuitively understand that it's better to have a bird in hand than a bird 0.75 3 years from now. So we're going to use this formula. I don't know if it has a name. We're going to use this kind of a cumulative future discounted rewards. You can sum it as sum gamma to the I R I. It goes from 0. And you can go to infinity without a problem. The reason you can go to infinity is because for any fixed value of gamma less than 1, if you did your calculus homework, you should know that this sum would decay towards, it'll converge. The added component goes to 0 fast enough that the sum converges. So we're going to use this formula. So our goal, going back to our question, our goal is to learn a rule that will tell us for any state what action to take, such as to maximize our total expected sum of rewards when the rewards are discounted in the future. Now notice that the value of this gamma could change our control strategy. If it's discounted very heavily, it'll bias us in what direction? Is this a gamma or isn't it? No, it is a gamma. So let's say for gamma that's very, very small, very close to 0, which direction would it bias us towards? Exploitation. If it's biased heavily, it's like living in a world with a lot of inflation. You want to get your money right now, you don't care what you're going to get a year from now or 2 years from now. If it's close to 1, then you care much more about the long-term effects because the discounting is not so severe. In the limit, if it is 1, then any finite loss is not important. You're optimizing sort of infinite tail. Shai?
The reward is a function of the input state of the action or of the output?
The reward is a function of the input state and the action. So let's formalize that. Let's write exactly what you're asking about. We have a set S of states. We have a set A of actions, and some of them may not be available in some of the states. And then S at time t is the state at time t, action at time t is the action taken time t, and then the reward given time t according to this formula here. And now, exactly answering your question, Shai, we're going to assume that a state at time t plus 1 is a function of the state at time t and the action taken at time t. The important thing about writing this down is to say explicitly that the state of time t+1 does not depend on anything else. It depends only on the state of time t and the action taken time t. Specifically, it does not depend on the state of time t minus 1, t minus 2, t minus 3. It does not depend on anywhere in the history. What do we call this kind of assumption? Markov assumption. This is the Markov assumption made by, it's a first order Markov assumption. It's a little different in the Markov model because there's this action part. But it's still a Markov assumption. This is still a memoryless or first order memory system. So it's not memoryless. Memoryless is zero order Markov assumption. It's a first order Markov assumption. And of course you can make a second order, third order, but you should know that you can take any second order Markov system and represent it as a first order by blowing up the number of states. The second function is the reward function, and the reward at time t is a function, call it r, of the same thing, the state at time t and the action at time t. So you can also think of this, of the pair, which state you transition into and how much reward you got, as a joint function of the same things. So the system decides together what state to transition into and what reward to give you. Or you can separate it into two separate functions and think about them separately. I'll try not to write so long, sorry. Now, two things we need to know about these functions. You can call this the transition function. I'm not sure if that's a common name, and you can call this the reward function. Two things we need to know about them. A, they don't have to be deterministic. They could be stochastic. So, same state, same action, could lead to different next states and different rewards on different days, different times. But it's still meaningful to say that they're a function only of these two things. So it cannot depend on other things. So other than these two things, the rest is pure noise or probability. It's not noise necessarily, but it could be a particular distribution function. But it's just a pure distribution function. There's no way of predicting it further. There's no way of reducing the uncertainty. So that's the first thing. They don't have to be deterministic. We will deal separately with the case when they're deterministic, when they're not deterministic. The second thing is, the learner may or may not know these functions. If the learner knows these functions, they are still faced with the problem of figuring out the optimal strategy. If they don't know these functions, the problem is harder. One of the beauties of reinforcement learning, of the beauty of the theoretical results, is that you actually don't need to know it in order to behave optimally. But again, with the caveat that it'll take you forever to learn to behave optimally. Okay. I want to introduce one more term, and that's policy. So policy is basically a strategy for behavior. A policy, which we'll use pi for, is simply a mapping from states to actions. If somebody handed you a policy, you could use it to move the system along. Whatever state you're in, you consult the policy to decide what action to take. Just like the reward and the transition matrices, policy does not have to be deterministic. Intuitively, you often would think that the optimal policy is likely to be deterministic. You know, if being in a certain state, one action is on average better than the others, and you should always take that. And that might be true. But the policy does not a priori need to be deterministic. You could imagine being in a certain state and saying, okay, I'm going to flip a coin. I think that in the first order Markov chain kind of world, optimal policies are always deterministic. But I can certainly imagine other worlds where they're not. think of two-person games, two-person zero-sum games. How much you get out of it would depend on your opponent, not only on you. And if your opponent knows what moves you're going to make, that might, change their behavior. So it leads to sort of minimax, and often it leads to, under some setups, it leads to deliberately choosing some things at random. Typically, we'll talk about deterministic policies. Now, for deterministic, worlds, namely a world where the state transition and the reward are deterministic, once you specify a deterministic policy, everything flows deterministically. There's nothing left. You can calculate, you can simulate it. You don't have to actually affect the system. You can tell exactly what will happen because you can just follow this chain of events. I'm going to start from the state, I'm going to consult my policy and do this action. I'm going to get this reward. I know what reward I'm going to get because this is deterministic and known. I'm going to move to this state and so forth. So if both these functions are deterministic and known, I should add that, in deterministic and known world, one could calculate the total reward discounted reward which is R1 plus gamma R2 plus gamma squared R3 R0 plus gamma R1 plus gamma squared R2 plus to infinity. Right? In a fully known and deterministic world, given a policy, you can calculate what your total expected discounted reward will be. We would call that the value of the policy. The value of the policy starting from some state S is defined as the total discounted reward we're going to get like this. And if the world is known and deterministic, then given any policy you can calculate this number. And then choosing the optimal policy boils down to just a optimization problem over all possible functions, over possible policies. That's still computationally non-trivial because there could be many policies. How many different policies could there be in a deterministic world? How many different policies? I promise to stop doing that if you give me the answer.
S squared.
Sorry?
S squared.
Why S squared?
Well, because for any state that you're in, you can do an action and then transition to any other state.
Your choice is among actions, not among which state you transition into.
So S times A then?
S times A. Somebody wants to suggest something else? So a policy is a function from the set of states to the set of actions. How many such functions are there? 8 to the power of s. The size of the range to the power of the size of the domain. So this can grow pretty fast. So even in the fully deterministic world, where policy is deterministic and the transition is deterministic and everything, it still may not be a trivial matter to find which policy is optimal. Although there might be a more efficient way of doing that. Dan?
Are we assuming some kind of long number of rewards as we go to infinity? Because you said that this would converge, but it's not guaranteed to converge. A necessary condition would be a bound reward.
Yes, you're absolutely right. But there is a bound reward because the rewards, if they are deterministic and they come from here, there's only a finite number of them. Right? You can write it down in a table. It's a finite number of states and a finite number of actions, so there's at most s times 8 different r values. The largest one of them is the bound.
Then why are we summing
We're summing to infinity over time. You can visit the same state again and again.
How about you get the same reward if you're in the same state as you make? Okay.
Right. Okay, so when we're in this situation, we will define our optimal strategy, we'll call it pi star, as the one that maximizes, you must think I'm obsessed with argmax, over all possible policies, the value of that policy, starting with state S, for any state S in big S. Now there's a little twist here. And that is, how do we know that the optimal policy would always be the same regardless of which state we started in? One could imagine that depending on which state you start in, optimal policy might be different. But again, because of the first order Markov property, because the system does not have long-term memory, it can be shown that under very broad conditions, the optimal policy is the same regardless of which state you started from. So just for you to have a good intuition of what optimal policy is, in a deterministic world, it's a very simple table that says S0, S1, S2, all the way through Sn, and it says what action to take. Here take action 7, action 2, action 9. You may not even have all the actions here. There's just a simple rule that says this state take this action, this state this action. One word about subscripts. We run into this problem all the time. The subscripts I used here are indexed over all possible states. There are, let's say, n of them, just like in a hidden Markov model. The subscripts I used here are indexed over time. So they look the same, but they're different. And if I were really careful, I would use somewhat different notation, maybe superscripts and subscripts. Or put these in parentheses. S of 2 is S of time equal 2. So the state at time t equal 2 may be any one of these n states. Same goes for the actions. When I wrote here A sub 2 or A sub 3, I meant the action at time 2 or action at time 3. The indices I used there are from a fixed list of actions, of possible actions. Okay, so we have this little twist here that says the optimal policy may be different depending on which state you start with, but I assure you it's not. For normal conditions with a deterministic world, the optimal policy is the same regardless of which state you're starting from. Now let's think about a non-deterministic world. In a non-deterministic world, you and I can start from the same state and follow the same policy, the same deterministic policy, and have very different experiences. You will be lucky, collect a lot of raspberries along the way. I will be less lucky, not many raspberries. I didn't do anything wrong. I just live in a non-deterministic world, and sometimes I will get lucky, sometimes I don't. So in what sense would one policy be better than another? I mean, if even the same policy followed by two different people on 2 different days could result in different rewards, and even in different places in the forest, because not only the reward function is non-deterministic, but the transition function is non-deterministic, so you can end up being in very different states. Even the same policy followed by the same person on 2 different days leads to very different experiences. Then how do you even suggest to compare 2 different policies and say which one is better? Suppose you try one policy and you try another policy, you get more raspberries. Is that proof that your policy is better? This should sound familiar to you, right? Remember our discussion of how to assess error rate of hypotheses and quality of learning algorithms? We said that just because you ran the same learning algorithm, you ran 2 learning algorithms and you ended up with a better hypothesis than somebody else, it doesn't mean your learning algorithm is better. Maybe you're just lucky with the training data being more appropriate for it. Remember that discussion? It's somewhat similar. Okay, so how would we define an optimal policy in a non-deterministic world?
The expected rewards is higher.
Yes, expectation is our key here. We will define the value in a non-deterministic world. This will change to the expectation of the same thing, gamma Ri. So you imagine starting from the same state, following the policy, accumulating whatever rewards, going to wherever the system takes you, doing that to infinity, then coming back to the same state and doing it again, and coming back and doing it again and again, and look at the long-term average of that. That's sort of an operational definition. A mathematical definition is the expectation of this stochastic process. Now, of course, we cannot operationalize, we cannot really do it many, many times, or infinite number of times, but if the transition and reward functions are known, even if they are non-deterministic, but if they're known, we may be able to analytically calculate what the expectation is. And then the definition of optimal policy remains the same. It's the policy that optimizes, that maximizes the expected reward. So this V value remains V, it's just that it means the expected value of the total rewards rather than the actual total rewards. Okay, so this is our setup. This is our definition of what we're trying to learn. Now, how are we going to learn it? How would you learn to play chess from just observing games and their outcome? How would you learn to search for raspberries in the forest by just observing someone taking steps and collecting raspberries? I want to point out to one thing that's different from our normal learning setup. In the usual learning setup, you get examples of input and output. For this input, this should be the output. This input, this should be the output. And therefore, if you encounter the exact same input in the future, you're in very good. It's very easy. You just do the exact same thing you saw before. The problem is more in the interpolation. What if you encountered something new that you've not seen before? How can you learn from what you've seen to generalize or interpolate or extrapolate to something you haven't seen? That's the normal setup. The setup here is different. You don't even get these input-output examples. Because if your output, if what you're trying to produce is a policy, nobody ever gives you a policy. All you see is specific action decisions made. And you don't even know if they were good ones. I mean, you can observe other people or yourself going through the space and making decisions and getting rewards, but at no point are you told whether a particular action that you took is a good action, it should be part of the policy or not. So you don't have explicit training examples. All of your training is very implicit. So, any suggestions? Please.
Well, by watching other people play, you can build your own reward system, or just fill in that table. And since let's say you have that, that would generate a policy, right? That if you have enough examples of people playing, you can basically know what to do in every situation. So you can get a policy for that.
Okay, so you're suggesting you build a table. What are the dimensions of the table? State?
All possible
States?
By all possible actions.
By all possible actions, okay. So, here are the states. Here are the actions. Action M. And then, what are you going to put in the table? Rewards. So this is the reward that you observed when you were in state I and took action J.
You should probably also have the state in which you go to, but you can...
Well, we said that the rewards are a function of the state you came from, not the state you're going into. So maybe you want to put the reward on the state that you came from and the action. So you were in this state, state I, and you took action J, and you got this reward. You put the reward here.
This is true. This is function R, basically. This is the state.
Okay.
You would need function delta as well.
So I have a separate table. Okay, so you're saying trying to learn these two functions by just having a table and recording from experience what happened.
But the problem with this is when in a normal learning situation you don't get to try out everything. So you can't exhaust the table.
Well, let's say you're in a situation where these two functions are known to be deterministic but are not known to you. Then I would argue that Dan is right. By using this procedure of just carefully recording what happened, you can fill out this table, and after observing long enough and of seeing all the combinations, you will have learned this function. If it's deterministic, once you see one entry, you know it's right. Right? And you can even imagine a situation when it's not deterministic, and you just have to observe it many, many times. And if you observe it many times, then in every cell, you can have a little distribution of R values. You know that when you're in this state and took this action, then you tend to get these kind of rewards. And if you've seen it 1,000 times in each cell, it gives you a pretty good estimate of the distribution in that cell. And the same with regard to the transition. So I would argue that your method is a perfectly good method for learning the reward function and the transition function. If they're deterministic, it will not take that long. If they're non-deterministic, it may take longer because you need to visit every state many, many times. There's a little problem, I'll get to you in a minute, there's a little problem, and that is that even if you observe something many times, there may be some transitions that rarely happen. So you may not learn much about them. But if you believe that all transitions and all actions are going to be observed, eventually, then just wait long enough and you'll learn that. Comment?
Instead of storing the reward, you store the value. So given a sequence of paths, you know the resultant value, you can given a path through the states, resultant value, you can reverse the function and compute the value of each state action pair.
So you suggest that we assign a value to each state action pair.
And so when you're at a particular state, you can weigh the two actions.
Okay, so I like that, but let me hold it back for a minute. I just want to talk about Dan's suggestion. Dan was suggesting a very simple algorithm for learning these two functions. I don't see anything wrong with it. My only concern is that this is really not what I was trying to learn, because I'm willing to give you these two functions. There are definitely situations where the two functions are known. So if they're known, you don't even need to go through this exercise. I'll just give you these two tables. Still, it's very difficult to know what to do, because you're not just trying to decide how to get the most reward in this step. You're also trying to think about all future continuations and how to get the most reward cumulatively into the future. That's where the problem becomes difficult. So all the combinatorial possibilities of collecting rewards along the way, let's suppose there are two ways you can go, and there's more reward here in this step, but this leads to more rewards later. How can you weigh them? How can you decide which one is better? So now back to your name? Eugene. The suggestion. Let's assign a value to each state. Let's do each state first. The value should capture the potential of this state going all the way to the future. So intuitively, what it captures is how good is it to be in that state? How much should you pay to be transported into that state? Formally, that value would be the cumulative rewards from that state on, properly discounted, if you follow the optimal policy. So if we knew the optimal policy, we could assign, in principle, a value, a potential for each state. What is it like? It's like when you evaluate a company, you think about the different market conditions, inflation rates, competition, regulatory, all the things that can happen in the marketplace. And then you say, okay, under these conditions, if interest rates go up and exchange rates goes down or whatever, what would be the projected net earnings of the company from here to eternity under good management, assuming they make good decisions. Okay? And then you can assume that, you can calculate that value or estimate that value, you can estimate that value under other conditions, and do it under all possible conditions, and then you may want to kind of average over all these conditions based on how likely they are to happen. So this is very real world, this kind of setup. So the value function is effectively this value function. When I said the value of a state under optimal strategy, optimal policy, it's the same as saying the value of the policy starting from that state. So what we can try to learn directly is this function. But not for any state, but for the optimal state. So what we're trying to learn, can you see this? Learn the function v pi star of s. It's a function of states that assigns to every state a value which is its potential for earning under optimal management, under optimal policy. Sometimes we will write it just as V star of S. Now, it's not a very big function. It only has as many values as there are states. If there are 10 states in your system, it's just a list of 10 values. But these 10 values capture everything you need. Because if we somehow manage to learn this true potential of each state under optimal management, then optimal policy will flow from that. How will it flow? Suppose we manage to learn the true potential of every state under optimal management, under optimal policy, which is what we defined there. How can we use it to decide what the optimal policy is? How can we use it to decide what action to take at any state? Please?
Maximum.
Pick the maximum.
Pick the action.
Okay, so we're in state S, and we want to pick an action based on S, and we're saying maximum over all possible actions, right? Of what?
That function given what state you end up in.
Of that function given what state you end up in. So that function is V star of ST plus 1. So this is ST. So the action to take when you're at state T is the one that maximizes the potential of the state you will end up in. And the state you end up in is this function, the transition function of the current state and the action that you're considering. Okay, so what have we got here? We're in state S sub t, we're considering all possible actions A. We know, in a deterministic world, we know, in a deterministic and known world, we know what state will end us in. It's given by this function. And then we look at the true potential of that state. And we want to choose the action that takes us to the state that has the highest true potential. Is that good? Tom?
You also want to add the value for the current state. No, I guess you don't need to.
The value of the current state. Well, the value of the current state. So the current state embeds in it the value of what you can get by starting from that state and moving on through other states, right?
Oh, but you get the reward when you take the action.
Thank you. I was waiting for that. We're missing the current reward.
Yeah.
Don't forget to pick up the dividends for this year. Right? So there is a reward. I didn't leave enough space here. Let me erase it because I want it to look nice. You get a reward by starting at state T and doing action A, and you get the future value, the value of the future state, delta, again starting from state sub T, taking action A. And we want to discount all future rewards because they are one timestamp into the future. So this is our gamma. So if somebody handed us the true potential of every state, the V star function, we could use that to derive the optimal policy, which is really what we're after. Under what conditions? Sorry? When R and delta are both known, where the transition and reward functions are known, do they have to be deterministic? Suppose they're known but not deterministic. can we still, given the V star function, derive the optimal policy?
You can draw a optimal policy.
Okay.
It may change.
Would it?
It's not deterministic that those values could change at any point in time. So we could run the state either at a time and it'll change.
Well, remember that we define optimal policy in the case of non-deterministic functions, non-deterministic worlds, as the expected value of the reward. So I would argue that even in a non-deterministic world, the V star values are fixed, and therefore the optimal policy is also fixed. You're going to suggest something?
I was just going to say the same thing. Our definition of V star uses expectations. So it's
Our definition of V star uses expectations, so that's true. There's only one change we have to introduce here. This is already using expectations, but this is not. This is assuming indeterminism, and also this is assuming determinism. So yes, given a state, V star is calculated over a non-deterministic future, but what state we're in here is not fully defined. So we will need to make some changes. The changes we'll need to make would be to take the expectation over all R and another expectation over all next states. St plus 1. So we only have to sum over all the possibilities in the current time step. Whatever reward we might get and whatever state we might end up in. And weight by how likely we are to end up in that state and how likely we are to get that reward. Once we take the explanation for both, everything else remains the same. So even in a non-deterministic world, having the V star function, the true potential under perfect management or under optimal management, leads to a clear, deterministic, computable, optimal policy. Let me show you one simple toy world, which is used in the examples in the book. So, imagine a world that has 6 states. These are the 6 squares at the top. And what we're trying to do is teach the system to get to the goal state, which is the top right. And remember I mentioned to you that we can do that by setting up our reward system appropriately, such that you get no rewards in any time except when you walk into the goal state, in which time you get a large reward of 100. You can walk into the reward state from either to the left of it or below it. So when you walk in here, you get 100 points. You walk in here, you get 100 points. Once you're here, there is no action that takes you out. You stay inside and you don't get any more rewards. All other states have actions that take them either to the left, right, up or down, as long as they stay within this rectangle. Okay? So this fully defines our reward function. Our immediate reward values. Now a policy will consist of a rule for every state what action to take among the possible actions. Because we set up the rewards to have a discount, time discounted rewards, the optimal policy would be the one that will take you to the goal as fast as possible, so that you don't lose interest, that you don't lose the value of inflation. Right? So what policy will take you here the fastest? Well, obviously if you're here, you should just go in. If you're here, you should just go as quickly as you can in. right? Don't go around. If you're here, go in. If you're here, you could go in 2 steps, either through here or through there. And if you're here, there are more possibilities. This is one, this is another, and this is a third. So there are actually more than one optimal policy. They're all equally good. Here's one optimal policy, you can see it here. Because the world is so small and deterministic and fully known, we can calculate the V star values, or the potential of each state under optimal management. Over there. So the potential of this state may be counterintuitively 0. If you're born in the goal state, you're not going to earn anything. You only earn things by getting into the goal state. The best potential is of the states that are adjacent to it. They have a potential of 100 because they're going to reap a benefit of 100 by taking the step to go in. States that are 2 steps away have a potential of only 90 because our discount factor gamma is 0.9, so you get discounted by 10% every time. So because it took you 2 time steps to get there, you got discounted once, and you're 90, and therefore the value, the V star value of this state is 0.9, or 90 times, 100 times 0.9 times 0.9, 81. Okay, so I showed you that if we had V star, we could from it derive very straightforwardly the optimal policy. My goal is still to learn V star. And one way to learn V star in a deterministic and fully known world is by simulation. Namely, maybe you start with some kind of V value and you imagine in your mind what would happen if you take one action, how much reward you'll get, and what other states you'll get to, and what would happen if you take another action. And you imagine all the possibilities, and you can, I'm not giving you the exact details, just very roughly, you can imagine some kind of an iterative procedure. Very much maybe like EM, where you start with some random guess of the true V values, and then you update them. Suppose you assigned a V star values to all your states, and then you observe that by being in state I, you could take action J, get a large reward, and get to state K, and you say, no way can state K have as little value as I assigned it. It must have more because I can always get to it from this state and do better. So you can use relationship between states to update and improve the accuracy of your V estimates. Okay? I'm not expecting you to know the details from my description. It was a very sketchy description. But the idea is that if you live in a deterministic and fully known world, and somebody hands you an approximate V table, value table, you could simulate the behavior of the system and make adjustments to the V table. It's not, maybe I should give you a concrete example. So suppose somebody told you there are 2 states here. This state is worth 387. This state, you're told, is worth 47. And you know that you can take an action from here to here because you have a deterministic and fully known action table. You know that by taking a particular action, say 7, you can get to here. And the discounting factor is only 0.9. Even if you got a reward of 0 here, no way can this be 47, this 387. Because if you're here, you just take a step to here, now you're worth 387. Yes, you had to take a discount along the way, so 387 times 0.9 is about 347, 348. So this state must be worth at least 348, because you could always go from here to here. Right? A chess position cannot be bad if you can have a move that leads to a good position. and in fact you can consider all other states you can get to. Let's say there's another state you can get to which is worth 250, but it gives you a reward of 50 here. Well, you could choose to go here. If you went here, you collect 50 along the way and you get 90% of 250. So 50 plus 90% of 250 is it more or less than this? Whichever one is more, that's got to be the value you put here. Right? So we can make a rule out of it. You can say no matter what value table you're given, you can start from one of the states and see if you can improve on it by considering all the states you can go to, all the rewards you can collect along the way, and what value you'll get when you get there. And knowing that you have the right to choose whichever one you want, you can choose the maximum one of them. Alright, so the formula would be the value of the state you're interested in, the optimal value of the state you're interested in, is the maximum among all possible actions of what you get by taking these actions. And what you get by taking these actions is the immediate reward for being in this state and taking this action, plus the discounted value of the future state. This is a recursive formula for V star. V star is defined the value under optimal decisions. And optimal decision means that you get to consult all possible choices from any state, and for each one you can simulate in your mind what reward you'll get, what state you end up in, and then you can add them together and decide which one is the best for you, and that's the value. So what this can lead to is an iterative procedure for improving on your V-star estimates. In fact, you could imagine starting from a V-star estimate of 0. All states are like, well, no, that won't work. Yeah, it will work because the R will break the symmetry here. So you can start with V-star of 0 and do that. But you can only do that by simulation or in your mind if the system is known, if the world is known, and you prefer also for it to be deterministic, otherwise you have more difficult calculation. What do you do when the transition and reward functions are not known? I guess we'll have to continue that next time. But what I'd like you at least to take from this home is that when the system is known, when the world is known, you can learn the V function iteratively using this recursive formula. When it is not known, we need a different trick. And if you read the book or the slides, you'll discover the trick. Okay? Alright, see you on Tuesday.